Good afternoon, everybody, and welcome to this webinar about our software dedicated to foundry casting, THERCAST. Today we will talk about the new version of THERCAST, and in particular the module dedicated to inclusion management. I am Olivier Jaouen, Technical Product Manager of THERCAST at Transvalor, and I will show you how to handle with THERCAST in order to deal with inclusions and how it can help you in the optimization of your casting process. To conclude this session, we are going to answer your question during a Q&A session. Furthermore, this webinar, is recorded and will be shared with all participants in a few days. Now the camera will be turned off and I will be back after the speech during the Q&A session. Okay, so before we start, just a few words about the GoToWebinar platform and how to operate the control panel. So you can use the orange arrow to minimize the control panel to the right. In the audio section, you can check for your audio settings. By default, the microphones will be turned off for all participants during the presentation. That means that there is not any exchange possible between you and I during the presentation. However, at any time during the presentation, feel free to type your questions. And during the final Q&A session, we are going to get back to you and answer those questions. Okay, so now we will continue for the presentation. So the agenda of the presentation is this one. So first of all, I will introduce briefly the notions of inclusions. Then I will briefly also present the model we have developed in THERCAST for the inclusion management. We'll see how to set up. Then we will have a live demo in order to see in live how to set up an inclusion computation and also how to analyze the results. Then we'll go back to the presentation and we will have the conclusion and perspectives. Okay, so for the introduction, I'm not going to make a course about the inclusion, but some words about the definition we have and what the impacts they have during the casting process. So inclusion are foundry defects. They appear during the solidification, but they can sometimes occur in the solid metal. They are mainly resulting from the presence of particles within the metal, so during the process. We did have different types of particles, so exogenous particles due to metal element mis-dissolution or precipitation issue during casting process. Exogenous particles due to the environment of the metal, like the scraps, sand or refractory grains, etc. Gas bubbles. And we can also denote different types of gas that may create inclusions, azote, oxygen, hydrogen. And regarding the impact on the cast product, inclusion can negatively affect mechanical properties. They can also create porosities or blowhole that are mainly defects due to gas inclusions, and they appear during the solidification. So on the right side of the slide, you can see some representation of different kind of inclusions, and also what are the different routes of these inclusions. So by a misnomer, I will call independently particle or inclusion in the rest of the speech, just to go faster. Okay, so how can we avoid inclusion? So I guess that's a very good question for all the casters. And the first thing is to find the cause and to anticipate it. So we have several actions that can avoid or limit inclusions formation. So one of them, so I have here a few lists of what it could be possible to do. So a metal treatment before casting, a use of overheated cycle, decreasing of turbulence flow during the pouring phase, so by working on the getting system design or limited the filling speed, or at least control the filling speed. Drying of mold between each cycle, precipitation process, so directly into the metal or at mold surface. We can also have access to vacuum gas extraction, so before the process, or directly vacuum casting process. We can also use some filters. So the use of filters is mainly to control the flow and also to clean the metal. But however, this is not always possible, and it could be quite interesting to have access to a simulation software with an inclusion tracking model that help you to understand and so modify and optimize the casting system in order to limit the inclusion occurrence. And that's why we have developed into THERCAST such a model. Okay, so some brief words about the model. So I'm now entering the parts quite technical, but don't worry, I won't go too deep into details. So, however, I guess that it's quite interesting to present what it is really solved in order to understand how it works. So the model is mainly based on fluid mechanics and drag force for sure. So it is dealing with this equation you can see here. So very standard equation of interaction between a particle and the fluid flow. We solve this model under some assumptions. So the first one is that the spheroidal shaped for the inclusion. We for sure deal with the particle velocity and the liquid velocity, and mainly the relative velocity between particles and liquid. So for sure, drag force and gravity force are taken into account. The drag force is taken into account the relative velocity and the relative Renan numbers. And also the drag coefficient, so CD in the expression, which has this expression because of the assumption we use, and also because we consider that the relative Renan numbers is smaller than 1. So that doesn't mean for sure that the fluid cannot be turbulent. That means that the particle is not creating turbulence into the fluid. So pay attention to this and not make the confusion. The model is of fluid flow is for sure turbulence if necessary. Okay, so that's nice to have some model that we can solve into the software, but it's not just to have some beautiful colors, it's also to be helping the user. So the model needs to be validated. And so we have mounted some validation cases. One of them is this one. So it's a simple one. We take into account a 1 meter H cube full of liquid metal. And in this cube, we have defined 4 sets of inclusions divided in 2 lines, 2 times 2 lines. The first 2 lines of what I can so-call big diameter inclusions, and 2 other lines with small diameter inclusions. So these lines are here in the representation. So we have 2 top lines and 2 bottom lines. And from this point of view, the left lines consist of big particles, and the right lines and the left lines are for the small particles. So another parameter in this cube is that we have imposed a vertical linear density distribution, so which is from 1,000 kilogram per cubic meter to 2,000 kilogram per cubic meter, so into the vertical direction. And actually, the distribution of the particle have respectively, a variation of density also from 1,000 kilogram per cubic meter to 2,000 per kilogram per cubic meter. So in that direction. Okay, so this is the context of the validation case. So what do we expect from this? So we expect that because the density of the particle corresponds to the density of the vertical direction, each density, each particle, sorry, will be at the final position respectively to the level of the density distribution. Okay, and also the big diameter inclusion should move symmetrically, the same for the small one, but with a different velocity. So this is the result. So what we see is exactly what we are expecting. Sorry. So the different particles are exactly distributed along with the vertical respectively to its density. And also, if I repeat the animation because it is going quite fast, we have the symmetry motion between the big particles lines and the small particle lines. So with this case, we can validate the resolution of this model. Okay, so how do we to do that actually? So some brief words about the setup. So when you activate action of metal in the interface, you have access to the advanced folder in which there is an inclusion button. And if you click on the inclusion button, this is opening a dedicated setup page, which is this one actually, on which you have all the parameters requested for the definition of the particles, and then activate the model of inclusion management. So you have a group section here and the particles by itself section. So the group is to define the group of particles, and into this zone at bottom of the window, you have the definition of the particle itself by the coordinates or nodes or whatever. You will show in the live demo how it works. And at the bottom, you have two main group of two parameters. The first one is the inclusion diameter, which is enough to define the volume of the inclusion because it's a sphere. And you have also the density for each particle. So this is the two first parameter for the physics, I would say, definition. And then in this section, you have two other parameters. It is the pilot ones. What does that mean? That means that you can pilot an each of the particle during the simulation time. So the pilot of these particles are following these different options. So you have the time, the process time, the filling rate, temperature, solid fraction, increment, that is quite interesting for the developers, I would say, or for just research case, and also the material or metal flow. This is actually activating the particle when the metal is reaching the position of the particle. Some few words about the units. We need to take care about the fact that here the diameter is mentioned to be in meter because the template I use is in meter Pascal and SI unit, whereas the density is in kilogram per cubic meter. If I would have used a millimeter, sorry, megapascal SI template, the diameter should have been entered into millimeter, and this would have been millimeter into the brackets, whereas the density remains in kilogram per cubic meter because it is SI in both unit millimeter MPa SI or meter PA SI. So in case of non-SI unit like the British units, it's inch and BTU. Okay, so what can we do with this setup? So we have here 3 examples of what is possible to get as results. So on the left, you have a cubic, I would say square cavity, so in which we have imposed a fluid flow, so driven by 2 gates. The first one is a big one here at the left side with a big flow rate, and the small one here from the right side. So these 2 gates are creating a fluid motion into the cavity. which is creating some main jets and also more or less big vertices depending on the time. And here we have a source of air bubbles that are driven by time, and also these bubbles have different size. So the size of the point is representing the size of the bubble. And so you can see that the behavior of each bubble is different depending on its size and the time it is released. So the big bubbles are going almost straight fully at top on the cavity, and medium and smaller bubbles are more or less entrapped into the fluid flow, so which is quite also expected. At the central case is actually semi-continuous casting for aluminium casting, in which we have here also a set of particles, which is this time also driven by time, and they are released into the fluid at different time of the process. And the color of the particle represents the size and density, which is different for each one. So also what we see is that depending on the size and the density, the trajectory of the particle is different, and we can estimate where particle can be found at the end of the casting part, and if we can have good or more or less good quality into the part if we take into account this kind of particles. On the right hand side of the slide, we have here an ingot casting, so in which we have also a set of particles who are piloting this time in filling rate. So depending on the filling rate, a set of particles are released into the volume of the ingot. So here we have two isosurfaces. The first one is representing the level of fluid into the mold, and the second one is representing the solidification front. And so what we can observe is that depending on the particles and the time it is unleashed during the filling, their trajectory are different, and finally at the complete solidification of the ingot we have a distribution of particles. Some of them are into the riser, which actually is not a big deal because the riser is finally cut from the ingot, but some of them remains into the volume. So in this case the ingot should present some defect, and the defects are more or less an issue depending on the size and the location of these inclusions. So now we'll see in live how to set up the different process. So sorry, my computer has been blocked, so I need to do this, and this is not actually the first one I wanted to show you. This is the first one. It is actually the case, the validation case. So as you can see, is a cube where we have defined an hydraulic computation in turbulence options. So it's full of liquid. And we have, so I select the advanced window as I was mentioning during the presentation. The inclusion button is giving access to the definition of the different particles. So we have here the group section and the inclusions section. So the group actually can be renamed. So as you can see, I have renamed each group with respect to the density of the particles and also the diameter. As I was mentioning, I have big particles and small particles. So actually the particles, the big particles have a bigger diameter than the small ones. And here we have the definition of the location, initial location of the different particles. And after here, as it is mentioning into the presentation, you enter the diameter, the local density, and the triggers, so the piloting. So by clicking on this button, you have access to the different options, and then you enter the trigger value. So in this case, the piloting is increment 1, so meaning that the particles are released at the beginning of the computation. One remark, we have the capability to enter one or more particle per group. So in this case, I have one particle per group. So why? Because each particle is different from the others. So this is how I can separate the characteristic of the particles. If I select one group with most of one particle, we can consider that the particle characteristic could be the same. Another thing is that actually we have the capability to modify the appearance of the particle by the colors and the size of the particle, and this is accessible by groups, meaning that in post-processing, all the particles belonging to the same group has the same representation. So if you want to have a representation per particle, it's necessary to set only one particle per group. Okay, so this is the rule how it works. Then here in this section, you can actually assign each particle to each group. So, okay, so this has been set here, so quite easily. Then the computation has been launched, and I have the results. So as you can see, once again, 2 lines with big particles and 2 lines with small particles. And here the definition of particles is with an increasing density from this point to this point, corresponding to the vertical description of the density imposed into the vertical direction for the cube. And then if I set the animation, so also, the representation of the different particles can be accessible from this folder, in which you can hide or display all the sensors, so sensor or particles actually, because the way to manage is exactly the same. And in this animation or representation, I have also activated this specific button, which is a button to show all time step. So this is quite interesting, because if I launch the animation, what we see is that we have access to all the trajectory of the particle during the process time. So this is another representation of the evolution of the particle during the process time, and it's interesting to see where and how it behaves during the solidification or the process time. So what we can see here is that we have exactly the symmetry between the big one and the small one, and the level of each one is respectively at the correct position in taking into account its own density. So this is really interesting to see. And so we see that the symmetry is really present, I would say, in this case between the small particles and the big ones. And so what we can see also is that with this distribution of all the position during the time step, we can see that we have increase of the speed and decrease of the speed at the final position, and so we can have a lot of information. So this was the first case I wanted to show you, and the second one is actually this one. So I have actually 2 cases. It is the same. It's actually one of the tutorial available within the package, the gravity die casting setup that you can find into THERCAST distribution. And actually, I have also exactly taken this setup, and I have just added inclusion. So in this case, what I wanted to simulate is the fact that at the beginning of the process, you could have some particles at the bottom of the mold. So in this case, so the case is a gravity die casting, so with metallic mold, but I have defined sand grains at bottom of the mold. So okay, could happen that you could have sine waves in the metacritic mode. Okay, this is just for the demonstration. And actually, I have here this distribution of particles, and I have defined for each different inclusion diameter different diameter. So each one is different in size, but with the same density. And in this case, the rules to activate the particle is the material. So that means that when the materials or the flow is reaching the position of the particle, it is entrapped and follow the fluid flow, and not follow for sure because there is competition between the particle and the fluid. Okay, so why two different cases? Actually, it is exactly the same, except that in one case I have defined in the property and in particular into the exchange coating 2 mm for one, and in the other case, sorry, it's the same, 0.3 mm for the other. So everything is similar between the two cases except this. So what do we expect? We expect that with the thicker coating, we have a slower cooling rate, so a longer solidification time. And the purpose of this comparison is to see how it impacts the behavior of the particles during the process. So I can pass into analysis mode. So the computation has been already computed, so performed. Usually we have access to different options, which is the custom action is one of my preference because we can directly put the setup of the appearance in a different case. So here the metal font is giving access to showing the fluid into the mold being automatically put in transparency. And then if I activate the animation, so hoping it's not taking too long, you will see how the filling is proceeding during the casting time, and also how the inclusion will behave depending on their respective size and the competition with the local fluid. So okay, the animation is launched. So you see that we have the filling from the melting pot here, and we have the solidification. So this case is the one with the big, thick coating, and this one is with a smaller coating. So I will do exactly the same in this section. So by passing into analysis mode, then okay, I have sorry, the same animation. Then I can launch the animation in this case. So it is also computing the same way. Just a few seconds to achieve the animation. And then what we will see is a difference of behaving between the two cases regarding the particles. So we have, so in this case, I have no the custom action activated, so I can activate it, and then it will appear the same as this side. Okay. And then, okay, so we have the pouring and so on, the same on the right, and so we have the filling and the behaving of the particles. So it's not really obvious to see this, so we can put the volume in transparency in the two case. Sorry, the behaving is not exactly the one I wanted to have. Okay, I go back to the ISO volume, so I put it also in transparency. And in this way, we see much better and much easier the particles. We can also put it in outline. So in this case, it's easier again. The same here. And what we see is that the particle is not behaving the same. So in the case where the cooling rate is smaller, the liquid remains liquid, the metal remains liquid longer, and then the particles are mainly distributed at surface, so in this case into the riser. Whereas when the coating is thinner, the solidification is faster. And in this case, some particles remains into the volume because they have been caught by the solidification, and so they cannot go till the top of the part and remain into the volume. So in this case, we can consider that regarding inclusion defect, the cast is proper. Whereas in this case, it's not that proper because it remaining some particles into the part by itself. So in this way, you can see that using the process parameter of the casting process, you can really simulate the behavior of the inclusion, and you can have access to some information that is helping you, to optimize the process if necessary. Okay, so this is the end of my demo live. I will go back to the presentation and then I will conclude. So THERCAST, as you have seen, allows to define inclusion by dimension and density. It allows to manage behavior of inclusion depending on process parameters, so temperature, time, material, liquid fashion, and others. And it allows to analyze and understand the behavior of the particle through the process times, and so it can give access to how review the design of the casting system if it's necessary. So it is really possible to optimize the casting process using THERCAST, and in particular this inclusion manager. But as always, it's not but, it's a fact. As always, we are trying to improve again and again our proposition for the customers, and that is why we have some perspective in order to improve again this model and actually feature. So we will add some models in order to automatically create inclusion during the process time, so with different rules. Some of them are that we will take into account the mold wearing or erosion during the process, so in case of sand molds or core. And in this case, the solver will automatically create particles depending on the different characteristic of the filling with respect to the fluid flow against the mold and so on. We will also add the capability to compute automatically the entrapped air bubbles. So depending on the case, in particular in HPDC, where air bubbles are quite a lot impacting the inclusions. This is quite interesting to have a possibility to automatically create the air bubbles. The same for the slag molds flux powder, so mainly for continuous caster and ingot casting process. Also models that will create endogenous particles, so based on the chemical composition, for example, or precipitation. This is possible. We will add, if what is proposing is not enough, we will have the possibility also to define its own inclusion manager by user model. So this will be also possible in the future. And another thing that could be also interesting is something that help for a posteriori computation, and in particular the capability to go back to the initial position from the final position. And this is something that would be also really interesting to do. Okay, so this is the end of the presentation, and I thank you a lot for listening to me.